All right, awesome. So I'll get started. And first of all, thanks everybody for joining. If you caught my presentation a couple of weeks ago at the Unconference, you're going to notice that there's a lot of new content here. Some of the same stuff that was on that presentation, but I front-loaded it with a lot of new stuff, mostly reflecting the new work that our team in the SPAR program did over the last couple of months. And I hope that's going to generate some new ideas and some new conversation here. The other, and so if Justice and Michael are here, I'm going to direct all the hard questions to them because they're the ones that did the hard work. And I'm also going to finish with a few advertisements for more work to be done. So if you want to do work for free for AI safety, stay until the end. With that said, so I'm going to be talking about distributed and planetary scalable AI safety. I've called this a seminar on probably safe AI. I felt like guaranteed was too strong, but hopefully safe AI was too weak. So probably I think it's a sweet spot. I'm an optimist. Okay, so in this seminar, we will cover, first of all, the motivation. That's going to be pretty obvious to you all, but I think it's important anyway. In particular, I want to talk about the kinds of AI risks that I think are important today, and the reason why I'm particularly doing this. I want to talk about our model for AI safety and how it connects to some of the other popular models that are being proposed. Then I'm going to do a deep dive on Gaia per se, which answers some of the questions that are opened by this approach, which have to do with it's our approach to AI safety is a model-based approach. So how do we get models, and how do we run models? How do we query models? These are both questions that we purport to answer. And finally, I'm going to invite you all to do work by admitting that we have still a lot more work to do, and potentially this is something that you are going to find interesting and want to talk about more. Great. So, well, the motivation is, if you've ever heard Daniel Schmachtenberger or anybody else talk about the meta crisis, that's really the motivation for me. And it's a problem of AI safety, but more than that, it's a problem of everything safety. And that is because, one of the factors of the meta crisis is this fact that we have increasing number of highly capable, inscrutable intelligence agents in the world. They are the problem is really that they are acting on a highly connected world system that includes the economy, that includes climate, food, biodiversity, biosecurity, cybersecurity, physical security, national security, and so on. And all these things are themselves connected. And to make matters worse, there's this little thing called Moloch, the god of coordination failures, that makes it so that, as a general rule, we can expect that the incentives are going to be for these agents to do things in ways that are misaligned with the provision of safety for humanity and the biosphere. So this is a total risk situation, and what Daniel Schmachtenberger has hypothesized is that there are two attractors to this dynamical system. One of them is a chaotic breakdown of all order, and the second one is, if you've ever heard of the Butlerian jihad in Doom, that's basically it. We kind of oppressively remove every, not just AI, but every sort of technology that could generate these risks and go back to some kind of 1984 situation. I don't want to get either of these features, and neither do you, so that's why we want to do something about it. And in particular, when we talk about AI risk, I claim that today's AI risks are less Skynet and Terminator and more things like, it turns out that self-driving cars are on average twice or so more prone to accidents than normal vehicles, and ideally we would slow them down, get them safer before we ramp them up, but that's not happening, and the risk to society increases more than linearly with this ratio. So this is a big problem. Another big problem is the speed and scale of autonomous weapon systems, and the speed and scale of algorithmic trading, which where the risk also in both of these cases that increases more than linearly with the size of the problem. And also, as a nod to Evan here, biosecurity. It's obviously one of the things that are most obviously risky, because it just came out of a global pandemic that, whether that one was caused by human agents or not, it's quite possible the next one is going to get caused by artificial agents. So yeah, in general, this is a question of misspecification, intentional or not, plus coordination failure, and those two things together add up and compound to catastrophic risk. Great, so nice little problem. Throughout what I'm going to be talking about, examples are going to be referring to one case study that has to do with the risk of overharvesting and ecosystem collapse, which is already happening today, but can be significantly accelerated by deployment of AI agents. So we're using overfishing as an example, because there's this great book called The Mountain in the Sea, where it has this whole subplot about AI fishing vessels. But yeah, the same applies to everything where you have like a tragedy that commons in some piece of critical infrastructure, whether that's ecological, or, as we talked about, the financial system, the security of the stability of the financial system, the stability of having functioning ecosystems versus this biosecurity thing. So yeah, this is just like one example where the dynamics are very clear, and I'm going to talk about that a little bit. And to me, like, what's really interesting about this is, again, that these are today problems where we already do a really shitty job at managing this risk, and introducing AI, even with the best of intentions, it accelerates and compounds these risks more than linearly. So these are important things that should be dealt with today. Multiple people have had more or less the same idea at around the same time, and this has coalesced in this thing that we're calling, you guys are calling guaranteed safe AI. Maybe I'm calling it too. And there's these three things that always tend to come together, which are world models, guarantees, or proofs. We're going to talk a little bit about that later, and safeguards. And there's different variations of those, and I'm gonna, especially with Steve in the audience, I'm not going to try to straw man or steel man in any of those, but I'll just claim that generally these are very related approaches, and they're all kind of generally aligned, but there's a lot of devils in the details that I'm gonna get to, just as a kind of a motivation for why I think that some of the directions that I propose with our approach are interesting and complement these other approaches. So again, with our case study here, you can think about having a company that has some stakeholders, maybe the owners, the policymakers, the CEO, the fishers themselves. This is a fishing company, and this company has deployed a bunch of fishing boats in the world. These fishing companies, as all food companies, they tend to be very increasingly vertically integrated and big and multinational and inscrutable and unaccountable. And so they have all these thousands and thousands of fishing boats in basically unregulated fishing in international waters, and what these fishing boat captains are incentivized for is catch as much fish as you can during your time at sea to make more money, to compensate the fixed costs that you have from all your fuel and your labor and so on. And that in turn leads to misalignment, leads to them making choices that are by and large not optimal for anybody. And this happens today, but if you start thinking about what I'm going to do with the fishing vessel that needs to be in the ocean all this time, I'm going to try to automate the hell out of it so that the costs are lower. So that's, like you're automating basically everything and putting AI everywhere. You're just going to put AI on an increasingly larger number of these fleets, whether fully autonomously or as recommendation systems, doesn't matter. So I'm going to talk about, we talked about those three things like world models, guarantees, and safeguards or gatekeepers. I'm going to first talk about the world model part first. And first, I'm going to claim that while, the obvious idea, which, as I said, a lot of people have had at the same time, is Bayesianism. And this is the way that basically that Banjo writes it in a blog post last year, where you want to have a model that allows you to make a claim about an agent action that, given a certain context, about a certain state of the environment and some prior data that you've collected, this gives you the conditionals, and conditional on that, you want to estimate that the probability of harm. You want to estimate the probability of harm and limit it to a certain threshold, epsilon. And there's a couple of problems with that. First of all, you notice that in order to be able to compute this, you have to compute it using a certain world model. And in general, there were some arrows here. The animations are not working. Okay, so there's a couple of really hard questions here. One of them is, well, where do these models come from? Like, how do you get world models that let you do this calculation? If there are multiple world models, which typically there are, even if it's just because they have different parameters between them, how do you weight those models? And we're going to talk a lot more about that. And finally, even if you have a way to weight those models, a principled way, how do you pick exactly what the right context is? So do you know that you're selecting the right ways and doing the calculation right? And there's also an axiological or values question of how to define harm. So I'm going to talk about that next one first. And I have no idea why the arrows are not appearing. This is super weird, but there should be arrows here explaining these things. So the main idea here is that you want to decouple and this idea that is widespread in finance. I'm going to be talking a lot about the financial system here and examples from financial risk management. One idea that is very common is that you want to talk about exposure or value as separate from the outcomes, from the things that happen in the world. So you want to talk about here your V here is a measure of value, and your L here is a measure of loss, which is negative of value. And what that allows you to do is set this thing called a preference prior, of which the logarithm is your objective, more or less. And in what we've done, what we like to do in our approach is to say, wait, a really nice way to model these how we want to think about values in a safety context is through this idea of satisficing agents that have they really don't like loss, and they like loss increasingly less when this is higher is better. So you get increasingly dissatisfied as your loss gets higher, but you don't particularly, like if you don't have a loss, if you have a profit or a positive outcome, you don't add an additional value to that. So basically you you're not balancing off your positives with your negatives. It's just kind of a constant once you get below zero loss, and that is a pretty nice representation of satisficing agents being indifferent between these outcomes that are positive. So if you have some function like that, then you can define this. There's a lot of things in this deck that are not popping up. So what I'm going to do is I'm going to click here. Oh, wait. Did you see that it disappeared? Oh my God, this is insane. Okay, what I'm going to do is I'm just going to get out of present mode, and I'm going to just show you the deck in rough mode. Okay, if I find out how to do it. This is why I'll never use this software again. Okay, so I'm going to see if I can zoom in. Yeah. Okay, this is what you get for free. Okay, so we really like this this active inference framework because it helps us think about a lot of things in a first principles way. And one of those things is it lets us think about risk exposure as a measure by free energy. So in this particular case here, we use a concept called the free energy of the future, which is a close cousin of expected free energy. And it basically gives us a lower bound on the expected model evidence. It lets us maximize reward while minimizing exploration, which kind of seems to capture the idea of risk pretty well. And in a fully observable setting, this just simplifies to something that is very close to things like conditional expected shortfall or the KL control objective. So we're in pretty much the right ballpark here. And one thing I wanted to notice is want you to notice that this is very much not a binary measure. Doesn't just care about harm, no harm. This does take into account how bad the loss is, and it does it in a principled way that's controlled by these K and beta parameters here. So one really important thing is, and this is one big reason why I care so much about where the models come from, is that model uncertainty matters a lot. In general, the things that we have in the real world are not normal. They do not have thin tails, they have very fat tails. And what that means is they behave like Taleb's turkey. This little parable here illustrates the life of a turkey. They're born and they're reasonably happy, and they have a model in their head which is the best fit to data, and that model is that nothing strange is going to happen to them. They're in the farm, and they're in this situation where the probability of harm, according to their best model so far, is 0 effectively, and it's 0 up until the point where they get a very nasty surprise. They are slaughtered for Thanksgiving, and afterwards the best model obviously is the model where the probability of harm is actually 1, but by then it's too late. And what you want is to avoid that. What you want is to not just choose the model that is the best fit to data so far, but to be smarter about that. But doing that is really hard, right? So if you just have the data, you're gonna make some pretty weird or bad model choices. So you will really want to have the context here. And I think that's really what people like Benjo mean by epistemic humility. And just the point here is that you really want to have as close to the right contextual model or set of models that represent what people that in the know that have skin in the game know about the situation as possible for you to get a model that's useful for risk management. And this is another thing here that I'm going to skip because I'm already running late. But just remember that because of this fat tail problem, estimating small probabilities requires a lot more data than you think. So, if you want to think about the probability of harm being being very low and being able to state that with a very high confidence. When that harm function, when that exposure has a thick tail, then you actually have to have a lot of data to be confident that that probability is as low as you think. So there's some technicalities that we can discuss, but this is just a general consequence of power law behavior and fat tails. Okay, so we did a little math here, and this is just to showcase some of the uses of this framework. We didn't get to everything that I wanted to show, but that's okay. So if you have a model of the world and of what's going to happen if your agents go out and do the thing that they're programmed to do, or that they're incentivized to do, which turns out to be the same, then you get to some conclusions. In this case here, we just use a pretty standard biological model for the fish population dynamics, and it turns out that no surprise, the profit maximizing agent will invariably overfish. It will drive the biomass from whatever the fish biomass from whatever its original state was to zero, as it tries to catch more and more. And even though it then realizes, oh shit, I made a mistake, I need to wind it down, it can never wind it down fast enough it can never justify to itself that it should wind it down fast enough to avoid the depletion of the fish stock. And this omega here is really just a way to look at the temporal discounting. If you have agents that see further into the future, that care more about the future, that understand that the future is important, they will score the risk higher faster. And so that we can see that already is an important factor. Okay, so now I'm going to switch gears a little bit and talk about, I'm going to skip from part 1, which is models, to part 3, which was safeguards. And I'm going to talk about 3 potential options for how to think about safeguards and their pros and cons. One of them is sort of like what I understood Benjo was proposing, which is something like real-time timekeeping. You want to calculate for every agent action. You want to have an actuator that before it decides whether to allow an agent's proposed action or not, it checks whether that action is safe by calling this function here, which calculates that probability, and it only allows the function to be performed if it's safe. And that is conceptually very nice, but it sounds like it could be pretty hard to compute this, including averaging over potentially an infinite number of models with high accuracy if you have very high actuation frequencies. And in addition, this whole problem of selecting context here, it seems underspecified. It seems like a potential attack surface. So this is something that we really need to think about. Are you looking at the right context for evaluating whether your model or your action is safe or not? The second category of safeguard are what I understand from David's current proposal, which is ex-ante guarantees. And this is basically you have, instead of doing the checking in real time, you're checking at deploy time whether the agent seems safe. And the way that you do it is that you, as he claims, you check for a set for every plausible but possible initial condition of the environment that the probability of the trajectory of the system with the agent being safe is high enough. So you want to avoid unsafe trajectories under every possible initial condition, which again has some pros and cons. It's theoretically looks pretty solid guarantee that you would want to have, but you need to sample or simulate trajectories over multiple complex world models like we did before, plus how many sample, but now for the entire trajectory, not just for the action, the result of the action, right? So ex ante for all possible conditions for all world models that you care about. And you need, as we discussed, because of these fat tails problem, you actually need a lot of sample trajectories, lot of data to have comfort that your condition here of epsilon is respected. And finally, generally, this family of plausible initial conditions of your system is going to be infinite, and because of chaos and everything else, it's actually very hard to sample from this and make any guarantees of extensiveness. The third option, which it's a lot looser and less guarantee-y, but it's basically what people do when they don't have formal guarantees, is what I'm proposing to do as well, is this sort of like risk assessment and oversight. So you have a deployment harness, and before you run an agent in a context, you ask the agent to propose a policy. You say, it says, I'm going to do this kind of stuff. And you have an algorithm here to check the risk of that policy. And if the policy looks okay, it allows it. If the policy doesn't look okay as proposed, you try to search for a constrained version of a policy that does look okay, that has a risk lower than the threshold that you chose. And if you couldn't find any, then you just return a default policy, and that's basically what you let it do. And basically, you don't let the agent choose its own actions. You have it pre-register the set of actions that you're going to do, and it only lets through actions that are within a pre-registered policy. And so again, in the case study that we discussed here, we implemented this strategy of policy constrainment, and it's a pretty simple one-dimensional case. So we can do line search over actions, but you can see here that for very loose risk thresholds, very large risk thresholds, you basically can the policy, it's to fish as much as you can for the first few time steps, and then you start getting constrained because more than that would generate overfishing. And the more you reduce your threshold, the more you get to the point where any level of fishing that you try to do here will generate too much risk, so it just naturally constrains your space of action. So not rocket science, really simple, but just the kind of stuff that you need if you want to constrain agent behavior and with a risk metric like this in mind. Okay, and now for my picking fights. And sorry for putting this in the slides, but I couldn't resist. So there was part 1, which is models, part 3, which was safeguarding, and there's part 2, which I said was guarantee or proof. And just kidding, there's no proof in the real world because the map is not the territory. And the alternative, which is in the paper that Davidad, Steve O, and a bunch of others published recently, it says that we don't want to have proof about the reality because there's no proof about the real world, but we want to have a proof, basically an auditable proof certificate that the AI satisfies the safety specification relatively to the world model. And that is definitely possible, right? You have a model, you have an AI, which is a piece of software, and you want to have a proof that it satisfies the safety specification. And my feeling is, which I haven't proved yet, but my feeling is that while that's possible, it's probably useless. What you actually want to do is, the best you can do really is have lots of induction over a wide variety of models and have robustness. That's the most important thing, which I'm going to talk about later. So, and the claim here is, which is not mine. It goes back way before, but it's been expressed by Taleb, is that there is a small world of models. There is a large world of the real world ecology and so on, and there is a predictable difference, which is this missing layer of randomness or model error, and you can correct for it to some extent by having hierarchical models, but ultimately there's always the risk that you're missing things. So you can capture that by looking at the tails and so on. And what you actually want to do is understand how exposed you are to errors, to those kinds of errors. because those are the ones that matter. And the example I want to give is, hey, turns out there's a bug in your gatekeeper code. And you don't really know where it came from, but it turns out that with some probability that you don't know for sure, you can estimate that probability, but you don't know it, and it's allowing any action to happen. So this, let's say this piece of the code here, where it's checking whether this is my code, so it can happen even in my situation, right? This piece of the code where it's checking whether the action is contained in the registered policy, it sometimes returns true when it shouldn't. So the ideal answer, of course, is this shouldn't happen. So you want to have proof that your entire stack is correct. And that means your code, your dependencies code, the operating system, the firmware, the hardware, everything about the data center where the thing is running, everything about the chip manufacturing and so on. And you know that it's possible to prove, if you have like a world model that's extensive enough, then you can prove all these things that I talked about. But at every time that you extend that model to cover more bases, you're building in more implicit assumptions, including you have to make assumptions about what are the probabilities of the capabilities of arbitrarily capable adversaries, right? And I think it was Steve Coy who originally made that point in quite this way. So thank you, Steve. And so, well, if you can't get the ideal answer, or like in practice, it's not gonna be very useful, then what do you do? And the safety engineer's boring day-to-day answer is, hey, you increase the margin of safety. So you don't need any assumptions for that, or any more assumptions than you already have. You just act on the exposure, right? You increase your threshold. So you look at the risk, the maximum risk that you can have under any policies that are possible in your system, and your current estimate of the probability of a faulty gatekeeper, which you can then pad, and basically make sure that your threshold is higher than that. And this actually works. This is basically how safety decisions are made, more or less, unless your policy space is such that your maximum risk is infinite. And this can definitely happen, right? There's definitely situations where you just like, there's no conditions that are safe for a system whatsoever. And this is weird. This is a really bad signal, right? This is when you have to actually acknowledge that you've gone beyond the point of modeling, and it's time for decision engineering. And decision engineering is this general concept that before looking at models, you need to look at your exposure, at your loss function, at what actually happens when things happen, and how it matters when you get it right or not. So in our framework that we proposed, we're proposing an exposure that is, as it is said, as it's written, it's unbounded from below and it's globally concave, which means that that you can have arbitrarily bad outcomes. So in principle, you can have, if the policy space is big enough, you can have arbitrarily bad outcomes. So infinite risk, and it's globally concave means that at least if you can consider this whole space here, then there's the worst decision, the worse the outcome, the decision gets more than worse, right? The incremental effect of a bad decision, the incremental negative effect of a decision increases faster than more than linearly with the outcome, the size of delta of the outcome. And the question is, can we change the environment, the rules of the game, the payoffs, and so on, such that the exposure is semi-convex on the left and even better bounded from below? And if we can do that, then we have what we call a robust system, which is a system where the worse the policy, the slower the exposure accelerates, and eventually it tapers off. So if you can have that, then that's really nice, because then you have to worry a lot less about whether your model is right, whether you've got every single bit proved, and you can just like focus on making your system robust to any screw ups that you and the modelers and everybody that's gonna come after you makes. And well, I mean, Formally, you can just do that by adding a delta here. So instead of log of p hat, it's log of p hat plus a delta. So you can conceive of situations where this works, but it's not always practically possible. Like if you want, we can talk about that later. And okay, so that's the framing the problem. And now with the problem appropriately framed, I'm going to be very quickly proposing what to do about it, specifically in the setting of where do models come from to perform this infinite sum here, how to weigh them, how to ensure they have high quality so that they should be weighed highly, and how to compute these probabilities or expectations efficiently and correctly. And what I want to say is that we're not going to get to all of it, but basically the architecture that I'm proposing here is an architecture that, again, is not just for AI safety, it's for everything safety, is for being able to do any kind of decentralized, crowdsourced, model-based prediction and assessment. And in a nutshell, it's actually pretty simple. First, this is quite obvious, but not that obvious. You want some kind of the distributed repository of statistical models that are justified by data. And this is in itself very nice, but you actually also want these models to be scored intrinsically by the network itself using some kind of protocol, and that protocol should be based in probability theory. If you have this thing, then 1 and 2 are what we call the model library, and so they give you the models and the model weights. And if you have those, then you can go one step further and query this model library. And the way that we prefer to do it is to do distributed simulation or sampling, which we can talk more about later. One thing that is really important to make this work is that if you have disputes about the models, then the way that you should resolve those disputes is by having competing models and having the system itself judge how good they are. So it's an embedded dispute resolution system. And the fifth one was the most controversial one so far, is really this idea of a knowledge economy, which is that the only way that we're going to get high quantity and quality of models and very strong data and evidence-based models is if model creators are incentivized. And the way to get these incentives is through monetizing the queries. So I'm going to skip over the details on all of these things, but I'm just going to talk about, again, like recap these ideas. So what I'm proposing as the Gaia network, what we've been building as the prototype implementation that we have, are really this simple. It's basically decentralized storage of world models, where these world models are, in our case, are probabilistic programs that are stored together with the data that they've collected that are relevant to that particular context, and therefore you have posteriors, right? You can compute posteriors for any query that you want. And because these models are connected to each other, you actually have a distributed model. So it satisfies that problem that it's better at other solutions that at satisfying that condition that I talked about, which is that you should pick models, you should weight models based on data that's relevant to the context. And sometimes that's not just observational data, but it's knowledge that the creator of the model has because they are close to the problem. So this is reflected here in number 2 as this idea of free energy accounting. The idea is that you can calculate the contributions of free energy, which is basically a way to measure the discrepancies in the model, the amount of the quality of the model given in explaining that particular context and things that are connected to it, given the data that's already received and compared to other models. So you can just do some math here, and we can talk more about it later. And the uptake is that Nodes that are less useful, with beliefs that are less useful to other nodes, get attributed low scores by their peers, and therefore tend to become ignored. There's a G missing here, obviously. Querying as distributed simulation and sampling, and again, this is something that Steve Coy has convinced me that is important. You want to have ways to query this distributed storage, so it's not just distributed storage, but it's also distributed compute. And basically, what you want to do is you want every node to simulate scenarios that are relevant to that to the context of that node. So if you're talking about, for instance, here farms or fisheries or parts of an economy, whatever, each node has data and models about a certain part of the world, and it it generates simulations based on a bunch of different possible scenarios, and that allows you to dynamically query, hey, what about this scenario? And share the answer back to the querying node. And basically what you can do is use this distributed querying pattern to basically do as much querying as you need, but we're going to talk a little bit more about that later. We already talked about dispute resolution, but I just want to emphasize that it's really important that this is not about opinion. This is just about using open competition and data to let peer nodes compare the usefulness and truthfulness of your outputs. And this is basically how open source project works. And it's really simple but really important idea. What's less obvious is that we also think that we're going to have money in the game here to have people have skin in the game, and we think that this idea of free energy accounting is also a very solid foundation for free energy economy. Data value chain is how we call it. And so the problem here is that pricing is intersubjective, and there's some really important questions about how solid this is, but we think that it's pretty solid, and I can have a conversation about it later. So yeah, and what this nets out, these are all supposed to be hidden slides, so I'm just gonna skip over them. And okay, I'm gonna quickly claim that what we're building towards is everything safety infrastructure, where we have where we combine specification generation and safety assessment for every kind of risk based on the same models, and therefore we can combine requirements that are generated for all different types of purposes, and use the same outputs for a variety of risk-related things. Some of which are things like safety reports to regulators, to your own stakeholders and customers, to investors and whatever, and as well as to the kind of stuff that we usually talk about in AI safety, like process controls and safeguards. Great. What's next? So it's actually really important to bootstrap this model network, because people in general don't know how to code, let alone write probabilistic programs. So what you actually want to do is find ways to pair up AI coders and modelers to either humans interactively inputting natural language, or scraping existing knowledge bases like the web for things like equations, semi-formal documents like field reports or whatever. And there's a lot of recent work about this. Joshua Tenenbaum's team put out a paper that does some of this last year. This one here on the left. A couple of guys published a proposal, really interesting on this on Less Wrong earlier this year. They call constructability. I highly recommend checking it out. And our own team did a lot of prototyping and initial versions of this for some kinds of domains last year as well. So it's definitely possible. So and it's a very safe way to use AI, because at every time you're gonna weight these models by the data anyway, so there's not that much risk. So bootstrapping a model network is something that we've been working on, and we think is really important. Another thing that we're going to want to work on, but I don't have time to work on, but if somebody that likes economics and this kind of stuff wants to work on, is what's the good enough for today way to do credit assignments and this knowledge economy thing. So there's a meta modeling question here of how do you make sure that you're interacting with trustworthy peers and get to that like trusted basis for an economy. And there's like a liquidity issue here. I'm not going to get into too much of that. Another problem is that distributed inference, the distributed computation that I talked about, making it scale you need to be a little bit clever, because otherwise you need you're gonna need order of the square of the number of nodes if your system is strongly coupled, as the real world tends to be. And so really the question is, Google only works because it has PageRank. What is Gaia's equivalent of PageRank? How can you bring down this squared complexity to something lower? And we have a very strong intuition, but it hasn't been tested, let alone published, that we can use GFlow nets to amortize this inference. And the idea is that each node maintains a surrogate of a neural network that's a surrogate of its own model, and of its neighborhood, everything that it needs to know about the rest of the world to answer its own queries. And this allows the network to amortize the costs and keep the network compute load at order of 1. And this sounds like a really good idea, except that this amortization is going to be somewhat expensive, so you're going to have to find some way to pay for it in advance. Is VC money going to pour into this so that we can have these nodes do all this compute up front? I don't know, potentially not. So I think it's really important to figure out the economics of this. I already covered this, so this should have been hidden. So there's a bunch of other stuff we want to do, but I'm going to skip. I'm going to thank all of our contributors so far that have done a lot of the hard work here, and claim that if you want to do probably the most important thing you want to do, you should be working on this kind of stuff. And if you want to create safe everything, one way to do it is to come and help us do it. So I'm going to stop. Thank you. I know I only left a little bit of time for questions, but let's talk. Thank you.
All right. So we will be now having a, yep. I think we'll just go ahead with anyone who wants to ask a question, just raise your hands. I think that should be good.
Yeah, all right. Steve, you were first.
Steve, you're muted.
Okay, there we go. Sorry. Thanks for the talk. Very interesting. How do you think about adversarial attacks in your framework?
I think they're very hard. Yeah. So I mean, the reality is that if you're talking about arbitrarily capable adversaries, there's not anything like in general that I think can be said about them, right? It really boils down to within a certain level of capability, whether that's computational constraints or resources or something else. In general, there's always kind of situations where you can contrive to generate worst case outcomes.
I might be next on the queue, so
yes,
just good. Okay. Yeah. So version control, right? You mentioned that you have like the Git world models. What are you like? How are you approaching the problem of like diffs for belief specifications?
What did you say before belief specifications?
The diff, like the get diff of a belief specification.
Well, so these probabilistic programs are just code, so you can just look at the diff.
Okay, you're not trying to do any kind of like structured diff that's like more appropriate to the quantitative nature of the programs yet?
Maybe that might be something that we want to do. I right now, the way that we're approaching it is basically you have two things. You have the commit history of code, which gives you the structure, and then you have the commit history of data, which gives you the evidence that you then input into the whatever approximate Bayesian inference algorithm you have to produce the posteriors.
Okay, great. Thanks.
You're welcome. Yeah, of course.
Next, we have Utkarsh.
Utkarsh.
Yeah. I think you showed a overfishing technique diagram, which discuss about the safety technique. So I just wanted to ask, like the arrows were showing and yeah.
Again, so this is what happens when you have too many slides. Hang on.
Yeah.
And of course, I'm doing it the stupid way. I should do it like this. Yes. This one?
Yeah. So
Yeah.
the arrows are showing an infinite policy, like flowing from the agent to the real world, and then the outcomes are flowing back. So I just wanted to understand, like, how does this represent the closed loop interaction between the agent's action and the real world phishing environment?
Yeah. So, well, you can think about the agent here inferring a policy or calculating a policy that's informed by sensor data and or informed by whatever, like history or whatever. And so it calculates a policy that it then submits to this risk assessment process. It gets back this go no go, and that go no go gets that allowable, or more generally a constrained version of that policy, which it can have like a what's it called, forget the name, but there's a reinforcement learning name for this, for like a barrier function, I think, is something like that. So it just like blanks out an area of the action space or the state space, and says you can't go there. And that is critically transmitted to the gatekeeper, so that the actions, whatever actions the agent then the brain, the neural network, let's call it, tells the actuators to perform, are always gated by that condition, right? And so this is not a fully real-time method, in that it won't work if you need to recompute everything from scratch every time that you need to take an action. So it really works if you have like a general sort of a general strategy, then you then narrow down into like context, more local actions as you go. Or if you just have a fire and forget situation where you have like a pre-calculated policy and just follow that.
Okay, thank you.
Of course. Steve, softball question, please.
Hey, Rob. One thing which your talk touched upon, but it's actually a general concern I have about framing things in terms of safety. There seems to be a sort of implicit assumption that inaction is safe, which suggests a great solution for safety: do nothing ever. However, in your very first framing of the problem, you pointed out, as Schmachtenberger and others have said, that where we go if we don't make any changes to our existing policies, which is slightly different than no inaction, leads to bad consequences.
Right.
So it's very different if you assume, well, I'm already in a safe place, should I do this thing or not? And I want your thoughts on that. The framing of safety under the assumption that you're already safe versus the assumption we got to get somewhere.
Yeah, I mean, I 100% agree with that. I think this example of the fisheries and resource management in general is a perfect illustration of that, where like the agents that we have in place already are are unsafe as it is, right? So the question is, and that is the case in general. Like the question of safety, to me, it is the appropriate word, but the framing is not how to do something new and keep it safe, but how to go from a situation where you are not in a safe place and try to find a pathway to get to a state that is more on manageably safe part of the safe space.
And closely related to that, I'm looking at your picture down at the bottom. If you operate one of these AI ships and to do everything properly safe so that it will do nice things, if your mechanism for imposing safety constraints does not apply to all of the other actors in the problem, it seems to me that your safety has once again gone out the window.
100%. Yeah, absolutely. So that is totally true. The framing here really needs to be what. Well, I want to say two things. I want to say what you just said is true, and in a bunch of cases, the higher number of agents of any kind that are operating, the more the risk grows, more than linearly, which often it's a combinatorial, so it's actually exponential. So, but often at least quadratic. So in this case, of the fisheries is actually a great example of this, where the competition between it's not even a part of our model, but the competition between companies or vessels or whatever actually leads to even faster exploitation than the monopolist profit maximizer, which has an incentive to fish as little as it needs to keep its profit margin.
Thank you.
So yeah, thank you everyone for the session. Thank you, Raf, for the great talk. Just wrapping up. For context, this is a monthly seminar series. You're invited to join for the next one by subscribing on the Luma calendar. And there is also a mailing list, newly renamed to a Guaranteed Safe AI mailing list, which will be also in the Luma information. And the mailing list is also a good place to discuss further the Gaia project and this presentation in particular. So yeah, thank you everyone for attending. I wish you a great day.
Thanks everyone for attending, and yeah, feel free to reach out. I'm on the mailing list. You have my email. Yeah, feel free to ping Orpheus or anyway, you know where to find me.
Thank you for attending.
Yes, bye.